Hi, I'm Alex from EDD Academy, and today we're going to be discussing the derivatives of the sine and cosine functions. For each of the sine and cosine functions, before we actually get into algebraically proving their derivatives, I want to see if we can figure it out from graphical intuition, from looking at a graph. So this right here is the sine function. And I want to look at certain points on its graph and see if we can determine the slope of the tangent line at those points, and maybe it can give us a hint as to what the derivative of the function is. So I'll set up a theta and slope table so we can look at the value of, say, pi, which is right here. So the slope of the tangent line at x equals pi seems to be, it's definitely negative, and it seems like the line negative x, so its slope is -1. So at negative pi, the slope of sine seems to be -1. We can look at pi over 2. At pi over 2, the slope is a horizontal line. The tangent line is a horizontal line, and that means it has slope 0. So its slope negative pi over 2. The sine function has slope, or the tangent line has slope 0. Looking at our 0 point, the tangent line here seems to be y equals x, which has slope 1. Looking at pi over 2, once again, the slope is still 0 because it's a horizontal tangent line. So at pi over 2, our slope is 0. And finally, at x equals pi, our slope seems to be, once again, -1. The tangent line seems to be the line y equals -x. So at pi, the slope of our tangent line is -1. This is definitely a pattern to me, and you might notice that this is actually the cosine function, as I have graphed here. So just graphically, we guess that the derivative of sine, so ddx of sine of x, equals cosine x. And on this next slide, I'm going to be proving it. So now I'll be algebraically proving the derivative of the sine function with the difference quotient. So we are proving that ddx, let's change the color here, that ddx of sine of x equals cosine of x with the difference quotient. And if you recall, the difference quotient says that the derivative of a function f of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. So if we apply this to the sine function, let's say that the derivative dx of sine x equals the limit as h goes to 0 of, plugging in our function sine of x plus h minus sine of x all over h still. You can see right here that this is actually a sign addition identity, which says that the sine of quantity alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. If we apply this identity to this term in the limit here, we get that. We have the limit still, as h goes to 0, of sine x cosine h, where x is the alpha and h is the beta in this situation. So sine x cosine h plus cosine x sine h. This is a quantity here. This is, once again, the result of this identity. And then we still have minus sine of x. And then this is still all over h. We can simplify these terms a little bit and write that we still have, note that we have to write the limit as h approaches 0 in every step, because that's actually what we're computing. And we're just simplifying what we're actually taking the limit of. So simplifying this a little, we have that sine x times, we can isolate, let's see. Yeah, so if we simplify this, it's sine of x times cosine of h minus 1 over h. Note, this is one of the special limits we looked at in the limit chapter, plus cosine of x times the other special limit we looked at in the limits chapter, which is the limit of sine of h over h. And if you remember correctly, this limit right here and this limit right here, you might have seen it as the limit of cosine of x minus 1 over x, and the limit sine of x over x. But nonetheless, this limit, we know by definition, approaches 0. This limit right here approaches 1. Simplifying this, we have that, once again, the limit as h approaches 0 of sine of x still remains, and then this term is 0, so times 0, plus cosine of x times 1. So simplifying this, sine of x times 0 is just 0, and cosine of x times 1 is just cosine of x, so 0 plus cosine of x, and we still have the limit as h approaches 0 of cosine x, but because there are no h terms remaining, the limit is just cosine x. Thus, our derivative is cosine x. So just like we did with the sine function, before we actually try to algebraically compute the derivative of cosine x, I want to see if we can determine it with some graphical intuition. And just like we did with the sine function, I want to look at different theta, different x values, and determine the slope of the graph at that point. So we will start with the value of negative pi once again, and you can see here that the tangent line is a horizontal tangent line, meaning it has slope 0. So at theta equals negative pi, the slope is 0. We can look at pi over 2 now, or excuse me, negative pi over 2, and the tangent line seems to be of the form y equals x. So that means it has slope of 1. So at negative pi over 2, the tangent line has slope 1. Now, looking at 0, once again, we have a horizontal tangent line, which means that our slope is 0. So, looking at the positive values, the positive equivalents of the values we looked at a couple seconds ago, at pi over 2, at the value pi over 2, it seems that our tangent line is of the form y equals negative x, meaning it has the slope negative 1. And finally, at pi, the graph flattens out again, meaning it has a horizontal tangent line of slope 0. So once again, we will look at these values here and try to determine the function that is the derivative of cosine x. And these data values correlates to the function negative sine x, as I have graphed as the red function here. So once again, this is just a guess. And we will be proving it algebraically in the next slide. So, like I said, just as we did with the sine function, we're going to attempt to algebraically prove that the derivative of cosine x is negative sine x. And specifically, we'll be using the difference quotient method as we did last time. So, once again, the difference quotient is, it says that a function, the derivative of a function f of x, equals the limit as h approaches 0 of f of x plus h minus f of x all over h. If we apply this to the cosine function, specifically, if we want to figure out the derivative of cosine x like this, we can write this as the limit as h approaches 0 of cosine of x plus h. Note, we're just plugging in cosine for the function f of x here, minus cosine of x all over h. This should look very similar to what we did in the sine example. And almost identical to what we did in the sine example, this right here is an identity. This is an identity, the cosine addition identity, that says that cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. If we apply this to our function here, we have that this simplifies to cosine x cosine h, where x and h are in place of alpha and beta. So cosine x cosine h minus sine x sine h. We still have that minus cosine x term. And this is all over h still. So once again, we want to try to rearrange this numerator and denominator into a form where we can cancel some terms with the special limits we learned. So we can write this as the limit as h approaches 0 once again of cosine x times the quantity cosine h minus 1 minus sine x sine h all over h. And because we have a subtraction sign in between these two quantities that are multiplied together, we can split up the fraction into the limit as h approaches 0 of cosine x times cosine h minus 1 over h. And once again, this is a special limit here, but we'll consider that in just a second, minus sine x times sine h over h. As we saw last time, this right here, this is a special limit, and this right here is another special limit. And we learned last time and in chapter 1 that this limit approaches 0 and this limit approaches 1. This simplifies our problem greatly. So if we rewrite this one more time as the limit as h approaches 0 of cosine x times 0 minus sine x times 1. This term here, cosine x times 0, is just 0, and negative sine x, or minus sine x times 1, is just minus sine x. So thus, we have the limit as h approaches 0 of negative sine x. But as we saw in the sine example, there are no instances of h here, so the limit doesn't actually do anything. So our derivative is just negative sine x. So d dx of cosine x equals negative sine x.